So this talk is about a lot of work I've done on characterizing ore minerals, especially using some advanced tools, looking at them at the nanoscale. And I'm part of a quite extended research groups, which is funded by the Australian Research Council, MEGWA, and also in some part OSCOPE. So at Curtin, I'm part of the Geoscience Atom Probe Facility, and I also work quite closely with the colleagues at UWA, and we have built together that research group called MEGI, looking at these high-grade gold mineralization intercepts. Okay, so the trace elements in all minerals, we all know the good stuff, which is in pyrites and arsenopyrites. We have quite some gold in there, and some ore deposits are basically just focused on this type of commodities, just the trace element, the gold hosted in the pyrites. But of more recent relevance, I guess, we shouldn't forget about all of the byproducts which are hosted in our lovely sphalerites. So in there we have critical minerals, which are byproducts. So in this case, indium, germanium, and gallium. These are some of these commodities when we hear much less about, because they are very small markets, but they are on these high priority government lists. So it's worth having a more deep look at their behavior in our ore minerals. Why? Because they're actually quite important for the high-tech applications of nowadays, whether it is touch screens for personal device, or LEDs for all sort of applications, or even network communication. So the fiber optics use a lot of germanium. Yes. But also for defense applications, these guys trying to like shoot you in the dark will use lots of germanium for their night vision goggles. So let's give them some. And this is becoming even more of an issue because China quite clearly understands what is at stake, and as a retaliation from some exports restrictions around manufacturing of computer chips from the US towards China. China said, okay, well, I'm going to restrict my exports of gallium and germanium. And if you want to play that game, we can go as far as we want. So since July, there's some export restrictions imposed by China. And building up on this, I think it's quite clear, and it's quite important for our Western societies to develop our own supplies of these quite atypical metals. Okay, so to really understand the geology of these type of commodities, we got to look at the fundamental processes which affect our ore minerals. So we establish when they are trace elements in ore minerals, but really, how are they hosted in our ore minerals? Are they, nicely peppered atoms within our crystal lattice? Are they actually forming nanoparticles? And what does that mean for the processes of mineralization, and so on and so forth? Another aspect which is quite important, I think, is what happens during our remobilization processes. Metamorphism, crystal plastic deformations, fluid alteration. What is the behavior of these trace elements during these processes? Are they simply staying in there? Are they mobile? Or are they, segregating to some particular features in our crystals? We actually really don't know the behavior of our trace elements in our minerals during these processes. We have good ideas, but with this list of trace elements expanding, we actually need to do much more work to determine those. Here, I actually hid something from you. I'll get back to it later on how this is relevant maybe for extraction and metallurgy. Okay, so you quite, I think by now you understood then, to determine these type of distributions, we need to look at the smallest scale we can. One tool which is particularly well suited to do this is called atom probe tomography. This complicated diagram here, what does it show? It shows analytical volume versus sensitivity. And atom probe sits in that field there. So we are looking at something very small, and we're actually quite sensitive in terms of detection limits. So our trace elements, we can actually see them, we can image them at a very small scale. To give you an idea of the scale, if that's a mineral, I made that diagram for monazite, but this is let's say this is a monazite. We can date that monazite using laser ablation ICP-MS, you may have heard of it, SIMS, or even EPMA. And this will be the analytical volumes when we use from these techniques. You see it? Atom probe is that tiny little dots there. And the volumes we are looking at are basically 5 to 6 order of magnitude smaller than any other conventional techniques. We're really looking at something extremely small, and within that volume, we can determine the position of atoms. Witchcraft, you say? I say, yes, it is. So this is how it works very briefly. What we have is a sharp specimen. So this is made of rock. We prepare these using another instrument called a focused ion beam, and we're able to make these tips, which are very, very sharp. Here, about 100 nanometers at the apex, and they can be a couple of microns in length. Then by applying a high electric field, we actually evaporate the ions from these specimens. The ions are just basically gonna fly off our specimen. They're gonna travel through some ion optics, and then they're gonna intercept a position sensitive detector. And then we can basically trace back from where these atoms impact our detector, where they come from our tips. We can also determine the mass of these elements using mass spectrometry. So basically what we have in the end is this. It's a point cloud of atoms, which are basically resolved in 3 dimensions. And each of these dots are single atoms. The scale bar is down here, 15 nanometers. This is maybe across 100 nanometers. And we can see, like in the example, quite a bit of heterogeneities. We have, copper enrichments along some sort of planar features. We have some iron exsolutions. And in there, we have some indium, which is also segregated in these planar features. So we're able to resolve that sort of complexities in our materials by looking at them at the nanoscale. Okay, one more thing, and I'm going to be quick here because otherwise we're going to be here forever. Have you heard of crystal defects? This is my new favorite thing. Crystal defects, in particular dislocations, are in a crystal lattice when we have half a row of atoms missing. So here we have a beautiful crystal lattice, and right there we have a mismatch, and we have some sort of a hole in our crystal. This is called dislocation. This is a very thin linear feature. These dislocations are important because this is how we can deform materials. So if we apply stress onto a pyrite or whatever mineral, that material is going to start to deform and bend and twist and so on. And these deformations, happen by the gliding of these dislocations progressively from one side to the other of the crystal. If you have lots of this gliding, you're basically going to form low angle boundaries or high angle boundaries. This is areas where the crystal accumulates these defects and start to bend and recrystallize practically. You can also form these dislocations by having a mismatch between 2 areas of your crystal lattice. So to accommodate for these bigger crystal lattice compared to these smaller ones, here we need a dislocation geometrically speaking. Okay, this is going to be relevant later. All right, so very quickly, we're going to go through some primary incorporation processes of our trace elements. And something you may be familiar with is oscillatory zoning. This very fine zoning when we see in many minerals, whether it is a magmatic mineral or a hydrothermal mineral. In this case, what is represented here is the gold distribution in arsenopyrites. And here we have the arsenic and the gold distribution within pyrites. On the right here, what we have is germanium distribution in sphalerite. And you see when in all cases, we have this very fine zoning and this complexity. So really, how do we explain that sort of textures? When we look at them at the nanoscale, we see exactly the same thing, but several order of magnitude smaller. So on the left, we have arsenic, gold, and copper in pyrites. And we see these very fine oscillations. The scale bar here is 20 nanometers. So we have like these variations of chemistry over a few nanometers. Same thing in sphalerites. This is copper, germanium, and gallium. And you can see then like we have these very fine oscillation of chemistry. So over the length of our crystal, we'll have millions, if not billions, of these oscillations. Some people claim that this oscillatory zoning is due to fluid composition changing, some sort of repetition of fluid flows. What I'm saying that is bonkers, because you cannot have billions of fluctuations over the crystallization of a mineral. This is more likely to be the results of some growth kinetic process where we have diffusion of elements towards the crystal phase. And as this mineral grows and the minerals diffuse to the location of the growth, we have this repeated pattern. So this is just a growth kinetic effect rather than a fluid composition changes. But that's not all. So over times, we observe things like this. In the same sample, we can either observe clumps of gold in arsenopyrites, or gold, nicely homogeneous within our arsenopyrites. And this again tells us that these nanoparticles of gold were incorporated during the growth of our sample. This is a sphalerite here, which is rich in germanium. And in this case, we don't see this oscillatory zoning. We see all these clumps of sodium, potassium, lead, and that sort of things. And we believe these are actually fluid inclusions. And in that case, the germanium is not hosted in our sphalerite, but it's actually hosted in these fluid inclusions in the sphalerites. So this changes actually quite a bit the way we think about incorporation mechanisms in minerals. Is it actually in the minerals or simply in some nanoparticles within the mineral? All right, remobilization processes are far more fun for me because they're a bit more complicated. And I'll start with pyrites. So this is an example here of a very weakly deformed pyrite. So the map here is called an electron backscatter diffraction map. Don't get scared, it's not that bad. What is it? It just shows you the crystal orientation of each of the pixels within this image. And the variation of colors basically tells you something about the degree of misorientation, the degree of deformation within that grain. What is plotted in white right there across the grains are the low angle boundaries. Remember, that's where all of our dislocations sort of pile up to accommodate for this strain. When we do chemical imaging of these using nanosims, which is a very nice tool which provides some nice chemical maps, we kind of see that maybe along this low angle boundary, we may have a hint of a gold enrichment. So we thought we will actually see whether there is really gold in there. And the answer is yes, there is, alongside other trace elements, such as copper, bismuth, and nickel. What we have is these linear features, which are basically our dislocations, and they enrich in all sorts of trace elements. So this means that during the deformation, during the migration of these dislocations due to stress, we have the trace elements following these dislocations. So the gold gets progressively enriched within these Low-in gold boundaries. We'll see why that matters later. All right, another case here. This one is a bit more complex, but pyrite especially, and gold-rich pyrite, arsenic and gold-rich pyrites, have this property sometimes of having these very funky textures. We have our nice oscillatory zoning like we saw before, and we explained what they were, but they also have these crazy, you know, like corrosion gulfs, which don't have any arsenic and don't have any gold. And we're like, oh, you know, has the gold left? How has the gold been moved out of these pyrites? So we targeted one of these boundaries to see really what was going on in terms of processes and how was the gold moving about. I could bore you with crystallography, but I'm going to move on. This is much nicer. So this is the atom probe results. So again, we have a point cloud. We have our arsenic-rich grain there, so on the side, and on the other side we have our arsenic pore, and right in the middle we have that contact where the actual dissolution was occurring. What do we see is that we got some nickel on just at the boundary there. Then gold is gone, copper is gone, but I don't know if you can see on the copper, but like every so often you have these like, you know, sort of small enriched domains. And if you rotate that atom probe needle, what you see is that they're basically aligned again in these dislocations. So in this example, again, we have trace elements enriched dislocations, and they are located right at that contact between the two domains. Now, maybe you're gonna have to believe me here, but if when I squint really hard, what I see is steps. Every time I got one of these dislocation, I've got a step in orientation of my boundary. Can you see it? I'm glad some people are nodding. What we came up with in that case is a bit of a different model from what is usually proposed to explain this type of reactions, where we have porosity and like fluids, and the front traveling across your direction, front traveling across your grain. Here we probably have some sort of dislocations migrating along that boundary and transporting all of the trace elements with it, including the gold. I could talk for hours about this, but instead I'll go to the next example. So I'm happy to talk more about it later if you want. The sphalerite this time, and the remobilization evidence we saw in sphalerites, which by the way is quite something new. Not many people have cared so far, but with the emergence of all these critical minerals, I think there's actually quite a bit of scope in doing more work there. This is a very simple example. We have a very rich sphalerite, very indium-rich sphalerites. It comes from a polymetallic vein, which is actually quite a high temperature. It crystallized at quite high temperature. And it's so rich that during the cooling, you basically had the spontaneous exsolution of zillions of clusters which are rich in indium, copper, and tin. So here we're probably touching at the phase stability of sphalerite and these trace elements in sphalerite. When it's hot, it can incorporate lots of stuff. When it cools, it sort of rejects them as nanoscale inclusions. This one, I'll show you a glimpse of that already. This is a sample from Germany, from a skarn deposit. And here, this type of textures in sphalerite where we have lots of lamella-like solutions have been interpreted to be from metasomatism of the sphalerite. So fluids and heat going through our skarn deposits and basically helping elements moving around. And what we saw again are these indium-enriched planar features. They are the composition of a mineral called rockosite. So it's basically not in sphalerite anymore. It is in these rockosite being indium, copper, sulfur 2 or something like this. Either like, as their own little lamellas or along boundaries, along chalcopyritic solutions. So quite complex in terms of observations, and we can start to think about what it means in terms of element mobility. And this will be the last example of tonight. This is a germanium-rich sphalerite, and this one was deformed and metamorphosed. So, we actually checked a similar deposit in a similar region of France. This is from France, which was the first time I worked on French samples. And we looked at a neighboring deposit which was not metamorphosed, and there the distribution was perfectly homogeneous. And then something which was actually metamorphosed showed this type of distributions with big fat clusters of briartite, which is a germanium sulfide. When I say big, they're probably at least 50 nanometers. And what happened is when you have, a density of large clusters, for me they're large, maybe for you they're not, but what happens is these crystals become more rigid. It's much harder to deform them. Basically, dislocations cannot migrate through your crystal anymore. They get pinned by these clusters, and the rich domains of the sphalerites basically become like little islands when you cannot deform anymore. So this is what you see on the electron backscatter map. These blue domains means when there is not much deformation in it, and that's where you have most of your germanium. So actually, here the metamorphism of these sphalerites and the formation of these clusters help in the preservation of our critical minerals in sphalerite. They will be much harder to remove from the crystal than if they were in solid solution. Yay. Oh, there we go. So quick summary before I move on to the last point. These minerals are actually quite complex. We like to think that they're not, but they are. And we see these valuable metals hosted in several ways. Even solid solution, this is the common assumption from most studies in the past where, we have these solid solutions, simples, problem solved, but not really. We also have nanoparticles. We have fluid inclusions, which are rich in some of these critical elements. And we have crystal defects, whether they are clusters or dislocations. I don't think anyone will contradict me on that one. Atoms are awesome. I think that's a given, right? Yeah. So what's the link with extractive metallurgy? Can we actually use this information to improve our metallurgical processes? Remember, we have our dislocations in pyrites. They are rich in gold. They are looking awesome, but really, are they an advantage or an inconvenience? It's been a while when we actually know that dislocations dissolve faster than bulk minerals. This is a nice study by Lasaga and co, where they basically did some modeling and experiments, and they show that this pit there was where a dislocation was. And in an acidic solution, I think this was the case of calcite here, the rate of dissolution of our dislocation was much faster than the bulk of our crystal. And other models show that basically, if you have a surface with dislocations, you'll basically dissolve out tubes very quickly of your dislocations, rather than the dissolution of the surface will be much slower. So if you have gold in your dislocations, you can actually preferentially dissolve these dislocations and collect the gold within them. We know then to extract gold from pyrite, you usually oxidize the whole thing and destroy all the pyrite so you can recuperate the gold. And that's great. I don't have anything against that. But when we think about things like in situ mining or mining of very low grade rocks, some selective leaching like this may actually be quite beneficial, especially if our pyrites are quite deformed. There's lots of these dislocations around, which have collected a lot of the gold during the formation. We could potentially find a way to extract that gold quite cheaply. I promised you I was going to show what was hidden behind there. And what is it is basically more of a conceptual model than I've been thinking lately of how this approach of looking at the nanoscale of minerals could be useful for extractive metallurgy. So with our beautiful sulfide, it breaks down, you smelt it, but then where do the companion metals go in that process? So this is particularly relevant for zinc smelting or even nickel smelting. In nickel, where does the cobalt go? And in zinc, where are the germanium and indium going? Are they in a slag in grain boundaries, or are they distributed throughout your slag materials? Are they forming nanoparticles? You could design a research program where you track down each of the metallurgical steps, each of the fumes, each of the dust particles, and the slag materials and the intermediate slag, if you have some, and actually study the deportment of these critical minerals down to the nanoscale to see whether they are in solid solution in some secondary minerals. Are they in grain boundaries of slag? Really, where are they? And that information could then be leveraged to design a secondary extractive process where we can get these out. All right, I'm just going to finish on that. If you're interested in that type of research, we actually have a funding, an access funding grant from OSCOPE, where we can do some critical minerals research. So if you're interested in that sort of things, don't hesitate to drop me a line and we can discuss further if that could be useful to you. Okay, thank you very much.